Hi everyone, my name is Avinaya Tripathi. I am a fourth year PhD student at Avinaya State University, working under the supervision of Professor Narayan Nethalat, and I am here to present to you about buildability assessment in 3D concrete printing. So, being a 3D session, like we have talked about 3D printing a lot. So, the mode of printing that we at ASU are currently using is a layer-wise extrusion. So, in layer-wise extrusion or in 3D printing, basically, because you don't have a formwork, you can't keep pouring in concrete layer over layer. There's a limit to which you can print, and then after it just breaks down. So, proper assessment of buildability is required for us to optimize the printing process, be able to print it without failures, without major deterioration. So, just gonna, these are some printing that have been done in general literature. So, what's a printable cement matrix? So, something that can be extruded. Here, pumping is was not a requirement because we didn't pump it, but again, extruders should be able to pump it out of the nozzle, and it should be stable enough that it will withstand its own weight. So, more layers can go over it. So, for printing, we need a cement mortar matrix that's soft enough for extrusion but stiff enough that it can handle its self weight. So in layer wise extrusion, we could do just a normal 2D path, extrude it upward, or we could do different models that like we have seen helicoids and stuff. So for a cement based mortar, there are some knowns and some unknowns that come into the print. Some are just solved by just trying the print out. So a proper material selection that you could reach the required height is required. A proper proportioning for different regions like lesser use of cement so that we use more of SCMs, more of aggregates is required, and proper mixing obviously will be required. So there are some fresh stress constant during printing. So lack of that mold results on the if the cement matrix becomes too soft, we'll maybe extrude 3 4 layers and it just collapse. So while doing a print, we don't want just 3 4 layers to be printed. But again, now how do we know how many layers does it print? Either by seeing the collapse, which after that we could do nothing. It's just done. So we'd have to reprint everything. So a proper and a more accurate theoretical model to analyze the buildability rate of a mortar, given any mortar, not just a mortar, but any printable mortar was required. So when we went through different literatures, there are different literatures about quantifying the buildability theoretically with yield stress, rheological parameters, some mechanical parameters on the green strength. So what we saw during in literature are like some cement mortars that have been tested for extrusion and all the things like, yeah, what defines an extrudable mix? Is it just the ability of it to come out, or its ability to come out as a particular shape that you require? So some mix could be extrudable, but once you place it, it will not retain its shape. So we needed something that retained shape. So there are a lot of modeling, 3D printing models and everything done there. But what we can usually see in literature is that cement mortar in its fresh state is characterized as elastic material. Technically, those term elastic means that you could most probably remove the load and this whole structure would go back to its original state before loading. But you could see that there are strains of around 5 to 10% induced on those structures, which obviously are not retractable. So it's more of a plastic. So the question came, is there a elasticity to the fresh concrete? And which obviously there should be. So what we initially did was we casted some big cylinders with proper casting, and we tested them under uniaxial loading, and we saw that there was an elastic portion to the fresh green concrete. So based on that, now there is not a model that was developed before with elasticity and plasticity of the concrete considered. So we had to develop a theoretical model and verify it experimentally. So the So while building, so there will be layers coming one above the another. So initially, when there are not enough layers in the top, the there will be no stress on the first layer. Once the second layer comes, there will be a certain stress growth because of the second layer superimposed on the first layer. So as this keeps on going, at a certain point, the first layer will exceed its elastic limit, and now it will act as a plastic material. So based on that stress growth and a bilinear stress strain response of the material, a model needed to be developed. And for this, now the printed structure before failure will be a multi will be in two different states, with lower portion being in plastic response regime while the upper state will be on an elastic response regime. So the whole work consisted of two parts, where it was predicting the failure through new analytical models and validating it through experimental print. So these are some equations. If I go into the details of it, it will take a lot of time. So I'm just gonna put them here. We could, if somebody has a question, I could talk to them about it later after the presentation. So these were the equations used for different failure predictions. So for the verification, we went with 4 different mixes to verify the model over different types of mix with different types of aggregate used, some with sand of the size of 0.6 mm diameter and lightweight aggregate in the range of 4 mm diameters. So for this, initially we needed to characterize the mechanical properties of the concrete. So for that, in literature again, usually the mechanical characteristics are taken out of casted cylinders rather than printed. And with printed, there will be a different response than a casted. We obviously know that. So what we did was we printed a big cube out of which we took out a 2x4 cylinder using a pipe, steel pipe, and then we tested this cylinders for uniaxial response. One particular thing that was required for us was, if there was not a proper preparation of the material, you will miss the first initial elastic response because it's a very small response regime. So making sure that the top surface was flat and the whole surface was in contact to the loading platen, so that the elastic response does not mix with the plastic response, was necessary. For that, we used the L scale to make sure it's perpendicular. We made sure the top surface is flat such that the whole loading platen will sit on the specimen. This is our gantry printer that we use for our print in the ASU facility. We did 2 different model checks for the print result experiment, a wall element and the hollow cylinder element. So these were the stress strain response obtained from the uniaxial test done on fresh cylinders that I showed before. So you can see initially there's not a particular big range of it, but there are elastic response for in motor even at initial stage, and there's a slight linearity till about 2 to 5% of strength, which we are calling here as initial plastic response. From there, we obtained all the elastic yield stress parameters, modulus, plastic yield stress, and plastic modulus parameter from the graph. This is the yield stress growth thixotropy experiment for the 4 different mixes. You can, so we have verified for a very soft material to a very relatively stiffer material here. So the model verification, as I said before, were done based on experimental results. Here it's a, for this it was not a type of failure verification, but it was more of a height of failure verification initially, for with the use of printing of a wall and a hollow cylinder specimen. So here you can see that there are 2 major different types of failure, one being buckling or crippling and another being plastic failure. So when the stress on the lowest layer exceeds the plastic limit yield stress of the material, it will be considered as plastic failure, and the blue line on the graphs indicate that. The green line points are the experimental results of it, and the red is the buckling failure envelope for different time periods. Here I forgot to mention that the prints were done it's 15 minutes, while the prediction are done based on material test mechanical testing of the green cylinders 30 minutes it's from mixing time. So here the x-axis shows the time from the mix, while the y-axis shows the height of failure. So you can see that this is for a wall and this is for a cylinder element. So you can see the predictions are quite close. They are particularly in the range of 10 to 20% error for the whole period of the open time. So when I say open time, it's basically the time to which a material most probably could be extruded and printed. So the accuracy of the model was quite good with the prediction. So it was verified over four different mixes. You can see there are two other mixes. So here we can see that at a point of time when you are printing a hollow cylinder, the failure type shifts from a plastic kind of failure to a buckling kind of failure. And we can see that the predictions also kind of follow that trend, like they deviate from a plastic failure envelope towards a buckling failure envelope. So in the previous part was the verification for the numbers, basically the failure height, but we had to verify that the model could predict the type of failure too, because how do you know if the height that we predicted for plastic failure is plastic failure and the buckling failure that we predicted is buckling failure? For that part we use DIC, so digital image correlation. For this what we did is we printed the wall element up to 4 layers, and using the silver background of the concrete as a process and adding white speckles on it, we started tracking the white speckles to see how the movement on the lower filaments will be when we start printing more and more filaments. So we could track the vertical strain growth on the lower filaments with more layers being added. The deep on the vertical strains are basically the time that the nozzle takes from moving from one layer to the other layer. So those were removed, and we corresponded the vertical strain with the print time, and we could see that if there's a plastic failure, there was a sudden rise of vertical strain in the lowest filament, or neither than if it was a buckling failure, we could see that the vertical strain did not have a sudden rise, but there was a sudden rise on the outside displacement, the W out of plane displacement on the elements. And I do not have that here, but again, there's a more detail to it, like how the analysis was done, how it's done, but the predictions were quite close. So whatever we predicted as a plastic failure through the analytical model, we saw that through DIC it was a plastic failure, while something that was more of a buckling type, sort of out of plane displacement and sort of buckling kind of failure. So in summary, if we develop the analytical model that could most probably give us the accurate prediction of when the failure will occur. You have a material, you have a mechanical testing for it done, then you could most probably calculate the failure height for your structure that you are going to print, and most probably optimize the print time such that you do not exceed that height within that period of time. So you could do a continuous print, maybe a slower but again optimized kind of print. You could stop before a certain failure could happen, so that way you do not lose the amount of work you have done for the printing already. So so with all the different types of models printed and different mix, till now we do see the robustness of the model. The further work on the model will be to test for fiber reinforced prints and different types of other prints to see if the model still holds for all the different things. But at least till now, the way we have used it, we see that the predictions for the analytical model are quite close to what we see during an actual print. So with that, I think I'm done. And any questions? Thank you.
Sorry, just before I start, I need to make some changes. Okay, that's good. No, that's good. I do apologize. Sorry. Okay. Okay. I'm sorry for what happened with technical problem. My presentation was into another room, I believe. My name is Mima Farzadnia. I'm from the University of Alaska. The previous talk was about freeze and thaw of 3D printing elements, and I was feeling the freeze and thaw from Alaska to California. Anyway, so yes, so the thing is that this is what I started when I was a research assistant professor at the University of Tennessee, and still in progress. And now a new PhD student is working on that. They're working with Dr. Zhou, that is already in the session too. So it's about internal curing of 3D printable cementitious composites using superabsorbent polymers. So this is we did the feasibility study actually, and now more detailed uh, research is going on. Like I said, that this is Reese is working on that. Hopefully next time he's going to come here and present that. I'm presenting on behalf of him, kind of. Well, the thing is that we all know about the problem, one of the major problems with 3D printing, and that is evaporation and drying, which can cause volume stability issues there. Okay, so because for conventionally cast concrete, we have formwork, and the thickness, or let's say the width of the sample, is not that high that evaporation causes a very serious problem, especially with higher water to binder ratios. Okay, but when we have lower to water binder ratio, and then we have the kind of like a larger drying surface, definitely we're going to have more evaporation, and we need to think about that. Like you see there, so in 3D printed concrete, the risk of evaporation in different directions. That this can cause higher porosity, and also if the water that is needed for hydration of cement is out, then we would have incomplete hydration. And then we would have weak interfacial bonds, impaired durability, lower strength, and lower volume stability. My previous, sorry, and my previous study actually showed me that SAP, or superabsorbent polymers, are a really good candidate to solve the problem. Superabsorbent polymers are actually cross-link polyelectrolytes that when they absorb water, they swell, and it takes about some time to release the water into the matrix. And this gradual release of water provides kind of like some functionality that we can use SAP as internal curing agent, as you can see there. And of course, the properties of SAP, the chemical characterization, chemical property of SAP would vary, and this changes the absorption and the desorption capacity of SAP, which should be studied if you want to use that in 3D printing. Again, this is from my previous studies. We figured out that SAP is a very important. It has an important functionality in controlling the evaporation. If we have the same water to binder ratio in concrete, for example, here we have water to binder ratio of 0.22, 0.18, and 0.22. And when we add SAP, actually, it reduces the water to binder ratio, it reduces the evaporation significantly. And this control of evaporation can lead to formation of higher density calcium silicate hydroxide or ultra high density calcium silicate hydroxide. The results are already available in the Cement and Concrete Research Journal. And so I don't want to talk more about that, but we did extensive research using nanoindentation technology to show that how this calcium silicate hydrate can change in density with the distance from SAP. So technically how SAP can help strengthen the calcium silicate hydrate in the mixture. So as continuation of our previous study, and as kind of like applying the advantages of SAP, we thought that this is a good idea to use SAP in the 3D printing. But there are major questions. Number one, how does absorption and desorption capacity, which can change with content, size, and molecular structure, affect printability of 3D concrete, which is a very important issue for us? How robust is a 3D printable mixture with SAP is, based on the variation in the absorption and desorption, and how does SAP affect mechanical properties and volume stability of the printed concrete. What I'm showing to you, like I said, is a feasibility study, and it only deals with one type of SAP, sodium neutralized acrylic type, with a median size of 450, irregular shape, and we developed our own non-proprietary mixture with a water to binder of a ratio of 0.31 and maximum aggregate size of 650, so it's kind of like a mortar. So this is the first thing that I want to share with you. We measured the absorption desorption capacity of SAP using T-bag test and also as per ASTM C1761, which is used for lightweight aggregate. And we realized that there's a huge difference in the absorption capacity when we are testing our SAP in water or testing our SAP in a mixture associated with the 3D printable concrete. It's like 10 times the absorption rate decreases. And as you see there, there's another important issue. It's about the time. If we assume that printing open time is about 30 minutes, if you look at those times, you will see that at 10 seconds right after addition of water to SAP or pour solution to SAP, let's say the retention or the water that is retained is about 35 grams of water per every gram of SAP. So it means that your mixture will dry out immediately after 10 seconds. And after 30 minutes, which is about our open time, that water retention goes all the way down to 4 grams per gram of cement. Okay, we have a problem during that time because the first 30 minutes is important for us, and it seems that the SAP sucks down all the water or a lot of the water that we need for flowability and the printability of our mixtures. And about the desorption of what you see on the right, so it has a slow desorption, which is quite similar in water and also the pore solution. And what happens, just like I pulled up one of the numbers there, 24-hour moisture content is like 97%. It means that within 24 hours, SAP still holds its water. And technically, based on previous studies, after first 48 hours, it starts releasing the water into the matrix, which provides enough water for the hydration of cement. So, but like I said, this affected our flowability. We use ASTM-C 1431 for now, just like a very quick estimation of our flowability and the flow range, and we realized that SAP at different contents, 0.2%, 0.4% of cementitious material, and 0.6% of the cementitious material decreased the flowability to some extent. But of course, this was for the fresh immediately after mixing. But after like 30 minutes, we had more constant values for flowability comparing control sample and the ones with SAP, which is mostly because the hydration of control sample was very quick, but SAP, because of the gradual release, the hydration was kind of like delayed. And the other thing, so we wanted to figure out, okay, what's going on exactly. So we checked we did hydration scanning, and you see the results here. Of course, I have only the results for control 0.2% and 0.4%. And as you see, as we are increasing the amount of SAP, the hydration is decelerating, and it's mostly because there is less available water in the matrix, in the mixture for cement to hydration. So that's one of the reasons that, I can say that flowability was flow of the mixture decreased. And we observed the same effect on the setting time. As you see, we used the penetration test ASTM 403 to measure the setting time at, and you see 500 psi and 4,000 psi as per ASTM are used to tell that what is the initial time and what is the final setting. Okay, initial setting and final setting. And again, you will see that the setting time is being delayed because of incorporation of SAP. And all this, they're kind of like the signs for us that, hey, when we have SAP, we would have some changes in the printability of our mixture, and we have to be worried about that. And one of the concern is that from zero time to the first 30 minutes, this absorption and desorption can change the printability. So that's one of the things that we have to overcome in this study. And but SAP, this is not from the printed elements. We are now, I mean that the results are out, but I'm not sharing it here. So like the phrase shrinkage, this is like the shrinkage, autogenous shrinkage of the associated mortar to our printable mixtures. And you can see that when we add SAP, what happens is that the autogenous shrinkage is decreasing, and even when we have like 0.6% of SAP, we have a little bit of expansion, which we can say that it can control it can compensate and inhibit the shrinkage in 3D printed concrete. So what we had to do later was to go through the printing of this 3D printable mixture with different parameters. We did the test like we did extrudability test and also buildability test at constant, let's say, printing parameters, but different nozzle diameters. For extrudability, we use a 10 millimeter nozzle, and for buildability, we use 20 millimeter nozzle. But the rest, all the printing parameters were the same, were kept constant. So the first issue was about the extrudability. As you see, number one shows the control samples. As we are increasing the content of SAP, our bits are becoming kind of like narrower, and this is because our mixture is kind of like drier, and so it can be extruded well, although we don't have any kind of like cut or break in our bits. So this is one of the issues that we have to be worried about or concerned about when we are using SAP. And the other problem that you see that this is the process of printing. We just use a small sample, like with 8 layers and like 10 inches of let's say the length, and we realized that there was an issue. The issue was that when we printed with higher content of SAP, like 0.4% and 0.6%, the top layers were like narrow because the mixture was kind of like dry, but the lower layers were flat. And it caused kind of like the average height to go down when we have 0.4% and 0.6% of SAP. All this exactly in the contrary to 0.2%. And the reason is kind of like here. The reason is that when we added more SAP, we needed more superplasticizer. So we added more viscosity modifying agent. The fact is that superplasticizer kind of like lowers the viscosity. It helps with the extrusion. It helps with the flow, but it's not really in favor of the buildability. So this is one of the concerns that we have now. Okay, so how to kind of like manage all this? But the rest, for example, about compressive strength, and you will see that the printed structure, the printed concrete, it goes as high as like 75 to 80 megapascal, and that shows that how robust our mixture is. So we don't have any problem with that. And also about the shear, we use the slant shear strength to kind of like represent the interlayer bonds. And this is a very effective method actually. And as you will see, anyway, we have lower interlayer bonds in our samples, which is technically because of the voids that SAP produce upon the release of water, of course, at later ages, okay? My previous results on SAP shows that over time, these voids will be filled, and it's not that effective. But anyway, what you see here is about 28 days. So we have a reduction in interlayer bonds. So that is also something we need to look at. And concluding remarks, this is a feasible study. Your comments would be really appreciated because it's a continuation of a very big project that Dr. Zhu and I are working on. So SAP reduced the flowability at first few minutes of open time, but later it was all right. SAP changed the printability parameters by delaying hydration, reducing the available water for flowability. Okay, and SAP increased the chemical admixture content. I don't like it, not only because of costs. I don't like it because during the open time, SAP can manipulate the viscosity and the rheological properties of my mixture, and I don't like it. So there's something I have to work and see that how I can kind of like produce a more robust mixture. And SAP decreased extrudability right after mixing, but increase extrudability kind of like within that open time. And also SAP increase the deformation of at the lower layers. That's a problem. Controlling superplasticizer in the favor of, let's say, the viscosity. And this is an issue. But we know that, and our results, recent results show that SAP can inhibit the shrinkage due to the evaporation, but like I said, still, that is something that I'm concerned, reduce robustness of the mixture. Thank you very much. I just want to give the credit to Reese our new PhD student that is working with Dr. Zhu, and Dr. Zhu that is already in this session. It is a question. I don't know if I have time. And again, I apologize for what happened before this.
Thank you, and we have time for a few questions. If any of the audience have any.
Yes. Yeah, exactly. Thank you very much. That's a very good point. Like I said, this is a feasibility study. We're looking at the content, we're looking at the size, we're looking at the molecular structure. And this is an acrylic type, but we have different types. Okay, so different types of SAP. At some point, we might need to synthesize our own SAP for printability purposes to control that robustness to increase the robustness of our mixture. Yes, yes. So far, we have worked on 3, 4 different SAPs.
Can you comment a little more about the other types of
polyacrylamide, the thing is that, yeah, for example, sodium-based polyacrylamides, uh, it's it's not it's important, and the thing is that so far this one kind of like working better than polyacrylamide, but the size also is very important. So we're looking at the size. So it's not only the linking elements, also about the size of the element. Yeah, that's it. Thank you, Isa.